Good morning, students. Am
Good
I
morning,
clear?
ma'am.
My voice is clear or any noise?
It's clear, ma'am.
Okay. So we have seen number representations, right? Last class. So as we know, we are working with now computer. So we wish to perform all the arithmetic any operations on computers. Generally, we deal with numbers. Numbers can be positive or negative, right? So when we are dealing with the numbers, a positive number usually indicated by plus sign and negative number is indicated by minus sign. That is a human indication, right? Because hardware implementations you come in computers, you must represent everything with ones and zeros, including the sign of the number, right? So hence it is customary to represent the sign with a bit that is placed in the leftmost position or leftmost significant bit of your number. Okay, that is universal notation. The most significant bit, if it is 0, we treat that the number is a positive, and if it is 1, we treat that the number is a negative. Okay, that is about how can we represent the two different numbers, which is unsigned numbers or signed numbers. Okay, in case of signed numbers, we may have positive and negative. So positive or negative sign is represented with the help of most significant bit in any number. Okay. So to represent those negative number, we have a few representations: signed magnitude form, signed ones complement, signed twos complement representations are available for representing the negative number. Okay. And it is clear that in sign magnitude form, the sign bit is separated, magnitude is separated. Okay, so while operating with a number which is represented in sign magnitude notation, you have to treat sign and magnitude separately while performing operations. Okay, that is the little ambiguity, which is complexity while performing any operations. So see, while developing operations in hardware, we have to take care of this concept, separating the sign bit, and only operations have to be performed on magnitude bit. That is in sign magnitude representation. Along with this, we have also another disadvantage, which is 0 has a two different representations available in sign magnitude form, which is +0 and -0, right? Let me share the screen. Okay. So we have seen +0 is different from -0 notation, where for +0, all the magnitude bits are 0, but the most significant bit which represent the sign bit, that is also 0. But for -0, apart from magnitude bits, the most significant bit that represents sign, that is 1. Okay, so this is a +0 notation in sign magnitude form, and this is -0 notation in sign magnitude form. What is this? మేడం నేను మళ్ళీ చేస్తాను. 1 minute, Amma. Why not? Okay. Okay. So, sorry, Amma. I have some internet issue. Share the screen. Right. So this is plus 0 and this is minus 0. This is how we represent whatever it is, plus 0 or minus 0. It's just 0, but in sign magnitude form we have two representation. So this is what another disadvantage with the sign magnitude form. So next representation for integers, unsigned integer, signed integers we are talking about is 1's complement. Even in here, in 1's complement, the negative numbers are represented by complementing each corresponding bit. Okay, right? So hence we'll be having negative numbers start from -1 to up to -127. We will be having the negative numbers. In even here also, it is true that most significant bit is 1 for negative number and 0 for positive number. 0 to plus 127 in positive range. Okay, but even here, though we did not separate the sign bit, but here for plus 0 and minus 0 we have two different notations. So hence this is also not suitable for implementing in computer hardware, because in any way, any representation we see, there should be one-to-one mapping should be there. Okay, for any particular number, only one and only one representation should be there, and it should be distinct and unique for a particular number. Okay, since that rule is not followed even in 1's complement, so this is also not considered. And final is a 2's complement, where all the disadvantages are eliminated here. Every representation, see, either plus 0 or minus 0, it is just 0, which has a unique representation, that is 8 zeros. So when we talk about 8-bit width, okay, and the maximum and minimum range that we can represent is plus 127 in positive range and minus 128 in negative range, and corresponding numbers in hexadecimal or like this. Okay, so this is how we can represent either in unsigned and signed integers we are talking about. What are the values here? Here are range from plus 127 and minus 127. All the numbers are of integers. This is what called integer representation. Okay, so now your numbers can be positive or negative. So hence we have of two different formats, unsigned and signed formats. In this, we learn how to represent either positive or negative in integer representation. Okay, right? If your numbers are integers, then I can use any of these formats to represent my number. Okay, so of course here, in addition to this sign, whatever are the numbers that we are dealing, it can be not just a positive or a negative, not just dealing with the sign. There will be a number which can be a fractional portion also. Okay, right? So I may have a number that may be a fraction, or it can be integer, or it can be integer fraction. Okay, we know how to represent integers. Now how to represent fractions we come across. Okay, how a fraction is represented. In normally we can use a decimal point to represent a fraction, right? So if my number is something like 23.45, okay. So in a decimal, this decimal point is there, right? A dot. This is used for representing fraction. Okay, this the dot, whichever is there, that is used for representing the fraction. Decimal point. This would we call it as decimal point. After decimal point, whatever is the number is there, that we used to specify the fractional part. Okay, so this is mixed value, integer fraction. This is a mixed integer, right? So if such numbers are there, how to represent, how to store it in your computer, now come across. Okay, so here we have used how to specify plus and negative with the help of most significant bit. Okay, similarly, now how to store this decimal point into a computer registers. Okay, so to store this, we have two methods, two representations again. Those are called, one is fixed point representation, another is, one is fixed point, another is floating point. So here this point, whatever it is, the term point, that refers to the decimal point we are talking about. Okay, so here the point in numbers format, either fixed point or floating point, that is what called decimal point present in your number. This refers to the decimal point. So fixed point notation means the decimal point is fixed. Okay, decimal point is fixed. Now where it is fixed? Okay, so in fixed point representation, we have two ways to fix the decimal point. To fix the decimal point, one is at the rightmost or right side of the LSB, which is nothing but least significant bit. Okay, rightmost of the LSB. See, for example, if I have 8-bit number, if my number is 8-bit number, I'll be having data bits range from D0 to D7, right? So D7, most significant bit is D7. Next successive bit D6, D5, D4, D3, D2, D1 and D0. These are my 8 bits of a particular number, if I suppose, right? D0 corresponds to least significant bit LSB and D7 corresponds to most significant bit MSB. Okay, so in fixed point notation, if my decimal point is fixed after LSB, okay, rightmost of the LSB, right side of my least significant bit, okay, right side of my rightmost significant bit, right side of my rightmost significant bit or else least significant bit. Okay, so if my decimal point is fixed here, it means all the bits corresponding to the left side of this decimal point corresponds to integer values. All the bits in right side of this decimal point corresponds to fractional point, right? See, if, for example, if I have a number like 11.01, if my number is something like 11.01, how you calculate this binary number into corresponding decimal? If you see, I have to apply powers of positive powers of 2 in left side of the decimal point, and I have to apply negative powers of 2 in right side of the decimal point, isn't it? Okay, right? So here I will apply a power like 2 power, what we call 2 power minus 1, right? 2 power minus 1, 2 power minus 2. Likewise, we apply in right side of my decimal point, and in this side 2 power 0, 2 power 1, all are positive powers in the left side of my decimal point, isn't it? Okay, so similarly here also, since there are no bits available in after right side of my decimal point, this represent a complete integer. Okay, this represent only an integer number. Am I clear?
Yes, ma'am.
Okay, right. So rightmost of the LSB, if my decimal point exists, there are no bits in the right side of my decimal point. In this case, all the bits represent only an integer number. So this is what called first way of fixed pointing, which is represent integer only. Okay, and in the second way, where my decimal point is represented at the left sorry, not left, actually it is left side, but it is how means right side of most significant bit. Okay, right side of most significant bit. See, in the same way, if my numbers are D0 to D7, okay, my bits are like this. So in a second way, where is my decimal point means here my decimal point is right side of the most significant bit. So this is what your most significant bit. So my decimal point is here. Okay, my decimal point is here, right? So because usually the most significant bit is used for representing the sign. Okay, so this is not considered till the end. Okay, so here my decimal point is available and it is fixed at this position. In this case, you will be getting numbers only completely fractional values. Okay, only fraction we can represent, which start from 2 power minus 1 to 2 power minus 5. 2 power minus 1 to 2 power minus 6, sorry, minus 1, minus 2, minus 3, 4, 5, 6, and 7. Okay, and this number will be having 2 power 0, and anyway this represents the sign. Okay, so this is how we will fix the fixed point. In fixed point notation, there is only this procedure available. Either we can represent integer or we can represent only the fractional part. Okay, where my decimal point is fixed at a particular location. So hence it is called fixed point representation, right? Next we talk about the floating point representation, which will be coming after a few more classes, where my decimal point is a floating. Floating means moving. Okay, so it is not fixed at one particular place. My decimal point is moving, okay, based on the value of exponent, and we'll be having three technical terms: sine, mantissa, exponent. Okay, so based on these values, the decimal point is floating. So hence we call it as a floating point notation. Obviously, the range of values that we can represent is very large when compared to fixed point notation. In case of floating point, those are obviously dynamic range of values is very large. Okay, anyway, in last class we have seen in integer the three possible ways of representing the numbers, like sign, magnitude, sign, one's complement and two's complement. Okay, so these are the two representation, fixed and floating point. Anyway, we don't have a fractional method of representing the number under our syllabus. So hence we have seen only the integer representation only. Okay, under integer, we have seen how the signed numbers are represented and how the unsigned numbers are represented and what is its range, and that's we have seen already. Okay, so next one more concept here that I want to introduce is overflow. So next concept is overflow. See, when we are dealing with n-bit numbers, okay, when I perform any operation, maybe my operation belongs to, let us suppose simple case, addition. Okay. 1 minute, amma, fine. 1 minute, I'll be back. So let us consider two n-bit numbers. When we are performing operations on those two n-bit number, a simple operation like addition. Okay. So when I add two n-bit numbers, you know that there is a chance of getting one more extra bit, right? When we add two n-bit numbers, I may get a chance of getting one bit extra. So n plus 1 bits may result in your operation. Okay, right? And whatever is that extra bit that we are getting while performing any operation like addition or subtraction, in any case, when we deal with, when we are doing the operation with the help of pen and paper, it is not a problem. We can accommodate any number of bits while we performing operation. Okay, but when we talk about a computer case, each number is fixed with an n bits and it is stored in a particular register, each of n bit width. Okay, so now you need to accommodate one more extra bit that results during the operation. Okay, so if I perform two number operations, if extra bit results, that has to be taken care properly, and with that bit I can complete my result. Okay, whether what is that extra bit represent. Okay, you need to store that extra bit in a proper way and you should complete the result, right? Okay, so what we call that extra bit? Any idea? Simple operations like addition or subtraction, while performing two n bits, if we get an extra bit, carry. Carry, is it correct? Anybody have doubt in that?
It's correct, ma'am.
Okay, if I am getting a carry, then what will be the result? We have to consider the carry for operation, for finding the total result or not. See, the significance of that extra bit will have two notations or two different names. One is carry, another way it is also called as overflow. Okay, so we are adding two n bit numbers. I may get an extra bit that is coming out of the range, out of n bit. That extra bit we call it as an overflowed bit. Okay, so how to treat that extra overflow bit? Okay, that completely depending on how what are the numbers that you are operating, whether you are operating unsigned numbers or signed numbers. So that will specify whether to consider the carry for your result or not. Okay, see, I will say one example. So let us consider two numbers in decimal case. Let us take two numbers in decimal, any numbers, some 98, no, okay, 98 in decimal and another number maybe 56. what is the result of these two when I add 98 plus 56?
154.
1
54.
154. Okay, so this is what your result. 154 is your result. Okay. Okay. Now I'm adding two positive numbers plus 98 plus 156, and I should get a result plus 154. Okay, this is what I am expecting. So if you want to do the same operation with the help of computer, how plus 98 is represented? I'm using a calculator. You can go by division and a remainder method. In decimal, 98 is corresponds to, in hexadecimal, 62. In binary, it is 0 1 1 0 0 0 right? So 62, how we can represent? 0 1 1 0 0 0 1 0. This is plus 98. And how 56 is represented? My number is 56. So this is how represented 38H. Okay. So or 0 0 1 1 1 0 0 0 0 0 1 1 3 8H 1 0 0. Okay. So these are the two numbers represented in binary, plus 98 and plus 56. You know, both are positive numbers, right? So most significant bit is 0, and here also 0. Okay. So now I'm adding these two numbers. So we used to go with a simple half adder, 0 0, least from start with the least significant bit. So 0 0 is 0, right? So this is 0 0 0 and 1 0 1 0 0 0 and 0 1 1 0 1 1 1 1, carry 1, and it is 0. Next again 1 1, carry 1, and it is 0. And what is this? We got a 1 here, right? Am I correct?
Yes, ma'am.
No extra bit coming out of the n bits, right? Okay. And your result is 8 bits only. Okay. And what is this value? What is this value? Value of the result. Okay. So to get what is this value? You need to first fix what type of numbers you are working with. Okay. See, if I say I'm working with the signed numbers. Okay. If I say my numbers are signed, right? So in case of signed numbers, I may have both positive and negative. Negative numbers are represented in 2's complement way. Positive numbers are all apart from irrespective of 2's complement way, right? So irrespective of the magnitude, only the sign bit is 0 for positive case. In negative case, 2's complement method we are using, and most significant bit is 1. Okay, that specifies the number characteristics in signed case, right? So this is what your result. And you from your result, it is clear that my most significant bit is 1. So the number is negative. Okay. So to calculate its value, I have to go by method of 2's complement, because since my numbers are if numbers are negative, it represented in 2's complement method. They're represented in 2's complement method. Okay. So it is clear my most significant bit is 1. So I have to go by 2's complement notation procedure. Okay. So for 2's complementing this value, complement all things 0 0 1 1 0 0, 1, 0, 1. This is 1's complement and add 1 to it. I'll be getting 1, 0 and remaining all are same. Okay, right? Now apply powers of 2. So this is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7. 2 power 6 is 64 plus 32 plus 4 plus 2. How much?
102, ma'am. 102.
How much?
102.
102. Okay. And we did this 2's complement method, right? And since this most significant bit is 1, so we got a result minus 102. Is it correct? Is it correct? It's not correct.
No,
right?
ma'am.
Okay, because we are adding two positive numbers and we are expecting our result should be positive only. Okay. And what is that value? It is plus 154. See, whatever is this extra one, actually it is overflowed. How we got this one? Due to the magnitude values. So these are the magnitude and this is the sign bit position. The magnitude of the result is overflowed onto the signed bit. Okay. So that will make my result negative. So hence it gets a wrong result. Okay. Result is wrong. In this case, we call that there is an overflow occurred. So that specifies the result is wrong. Okay. So in case of signed numbers, it is clear when we add two positive numbers, I should get only positive result. Okay. Because my result is more, which is plus 154. But with the help of 8 bits, I can represent only a maximum plus 127. Beyond this, I cannot represent. Okay. So the result is exceeds the maximum value and it goes by a procedure what called wraparound condition. Again, it starts from minus 128 in this manner and it reaches to minus 102 to get my result. Okay. This is what called wraparound condition. This is what happening in fixed point notation and this specifies the occurrence of overflow. Okay. Right. This is in case of signed way. But if you treat that my numbers are positive, my numbers are unsigned. Okay. If I consider that my numbers are unsigned, there is no concept of sign here. All the bits will participate in magnitude. Okay. You have to apply powers of 2 in the whole way. The addition is same, whether it is signed number or unsigned number, the addition is same. Only the user has to treat based on his number representation. Okay. So based on his type of numbers. If he assume that he is dealing with unsigned numbers, then he will apply powers of 2 in whole the values. So then I will be getting plus 154. Now apply powers of 2 here. Okay. With the help of go by calculator. You got result 10011. 010, right? So in binary, sorry. So in binary, your result is 1 0 0 1 1 0 1 0. Okay. So how much is this? This is in decimal 154. Okay. So if you treat that your numbers are unsigned, all the 8 bits will participate in magnitude. I'll be getting the correct result plus 154. Okay. If I treat my numbers are negative, then based on the most significant bit, you have to decide. Okay. Right. You will get based on the most significant bit, you complement and get the result whether it is suitable or not. In that way, you need to decide whether the result is correct or not. Okay. So this is what called overflow. Overflow will occur only in case of signed number operations. Okay. Overflow occur only in case of signed numbers. In case of unsigned numbers, the whatever is the extra bit that is coming out, we call that as carry. Okay, we call that as carry, but in signed case, we call this as overflow, right? See, we have done addition of two positive numbers. Similarly, overflow may occur in a case where we perform addition of two negative numbers. Okay, so whenever we add two negative numbers addition, if we get a positive number as a result, then that also said to be overflow. Okay, right? See, for a simple case, let us consider numbers like -1. Um, -1, how it is represented in 2's complement way? FF, 8 ones. This is -1 in 2's complement way, right? And the next number, let us consider minus 128. Okay, this is the maximum. One is -1 and -128, least number that we can represent. Okay, so what is -128? It is 1 0 0 8 zeros, 7 zeros. Okay, when we add these two, you should get -129, which we cannot represent with the available values, right? So when I add these two, you perform addition, I'll be getting all in 1 means 1 0. This is what we call extra bit out, and all are 1s. 0 1 1 1 1 1 1 1, right? Okay, so 1 1 is 1 0. This is, we got now 9 n bits and one more extra bit here. Okay, right? See, what is this value? I'm saying my numbers are signed numbers. So here I got a most significant bit as 0, which represent a positive number. So what is the result of this number indirectly? The result here, it is a positive and all ones, right? So which is equal to plus 127. Plus 127, and we got an extra bit out of the range. Okay. See, here we are adding two negative numbers and we got a positive number, which is incorrect. This itself says that the occurrence of overflow. Okay, right? See, here there is a chance of overflow, and here is also there is a chance of overflow. Right? If I see in the unsigned case, I assume that these numbers are represented in unsigned case, then all the bits will participate in magnitude, and the value of this number is 255, and value of this number is, what is this value?
128.
128. Now add these two. 255 plus 128, how much?
383, ma'am.
255 plus 128, 383. In binary, see, in binary, we got the same result, this one. Okay, how we got 383? We have participated, these extra bit, we treat that it as carry and we apply powers of 2, then we get the correct result. Okay, right? In signed case, in signed case, we term the concept of overflow, but in a unsigned case, in unsigned case, all the bits will be considered for magnitude, including the carry. That will gives you the result. Okay, there is no wrong result in case of unsigned case. Only in signed case, if overflow occurred, we will neglect the result, saying that the result is incorrect. Okay, see, in this case, excuse me. Very sorry. Very sorry. Okay. So in unsigned case, whatever is the extra bit that is coming out of n bits, we call that as carry. That will also consider for magnitude to get your correct result. But in signed case, whatever is the extra bit that is coming out is not said to be carry. We call that as overflow. Okay. In this case, we got extra bit 1. In this case, we got extra bit 1. But here in this case, we don't get even extra bit. Even then, we got a carry here. Okay. But here, we got an extra bit. And we are saying overflow occurrence. Here, though there is no extra bit coming out of n bits, even then we say that there is a overflow occurred. Okay. So in these two situations, here two positive numbers are added, here two negative numbers are added. There is a chance of getting overflow occurred in these two cases, right? Let us consider in a simple case. In a simple case where two positive numbers like 2 and 3, positive plus 2 and plus 3 are added. Very simple case where plus 2 is nothing but 0, 0, 0, 0, 0, 1, 0. Plus 3, 0, 0, 0, 0, 0, 1, 1. So I'll be getting result obviously. How much is the result? 5, right? Plus 5. 0, 0, 0, 0, 1, 0, 1. Simply plus 5. Okay, there is no extra bit out of this. The result is correct. Similarly, go by negative numbers, minus 2 and minus 3. Minus 2 is how much? Minus 1 is all ones, since they have to be represented in 2's complement form. Minus 2 is 1, 1, 1, 0. Similarly, minus 3, 1, 1, 1, 1, 1, 1, 1, 0, 1. Right? Minus 2 and minus 3. You can check even with the calculator. FF, FE and FD. Correct. Minus 3. Now perform addition of these two. Two negative numbers we are adding. What is the result we are expecting? Minus 5. Right? Minus 5. This is 1 and this is 1. This is 1, 1. 1, 0. And this is 1, 1, 1, 1, 1, 1, 1, 1, and 1, 1. Here we got a carry. Extra bit. And what is this? This is F 1, 0, 1, 1. FB. FBH. Okay. So this is nothing but minus 5. See, minus 1 is FFH. Minus 2 is FEH. Minus 3 is FDH. Minus 4 is FCH is minus 4 and minus 5 is FBH. Okay. Right. So here we are adding two negative numbers. This is negative and this is negative and my result is also negative and it is minus 5. We can represent within n bits. So the result is correct. Right. Here we are talking about plus 2 and plus 3. In that case also plus 5. We can add plus 2 and plus 3 and my result is plus 5 here. This is also correct. Right. But here, in this case, we are adding two positive numbers. Result is wrong. And here we are also adding two negative numbers, but the result is wrong. Okay. How can you conclude when overflow occur? Right. How can you conclude here? when there is a chance of overflow. By observing these 4 cases, we are adding 2 numbers where my result one is within the range and another without, I mean, which beyond the range. Okay. So in these, by observing these 4 cases, we can conclude that there is a chance of overflow occurred. See here, check here. We got a 1 means 0. We got a carry. We got a carry into MSB. We got a carry into MSB here, and we don't get any carry out of MSB in this case. Okay. So carry into MSB and carry out of MSB, you have to concentrate. So in this case, in first case, there is a carry into MSB. Okay. And but there is no carry out of MSB. And in second case, in this case, there is no carry into MSB and there is no carry out of MSB. So both are 0, 0. And in this case, -1 and -128. See, if you observe 1, 1. Okay, 1, 1, here 1. We got a carry out, but there is no carry in. Right? So we got a carry out, but there is no carry in. In this case, -2 and -3. -2 and -3. What is the result? See, in -2 and -3, there is, we got a carry into MSB and as well as carry out of MSB also. Right? So we got carry into MSB and carry out of MSB. So in which case we got overflow by observation? By observation, here we got overflow. Overflow is 1. And here +2 and +3, this is my second case. There is no overflow. And this is my third case, -1 and -128. There is also overflow. And this is my fourth case, -2 and -3. There is no overflow. Okay. So can you justify when the overflow occurred by observing the table? When carry into MSB
carry
and
in
carry
and carry
out of MSB are not same, then there is a chance of overflow. Okay. So now overflow can be detected when an XOR operation is performed between carry into MSB and carry out of MSB. If overflow, if the operation result is 1, then I can conclude that overflow is occurred and the result of signed operation is wrong and we should not taken for consideration. And the result is wrong. It is clear. Okay. And this method of observing the result should be followed when you assume that you are working with signed numbers only. If you assume that numbers are signed numbers, then the whatever is the bit coming out of MSB is treated as an extra magnitude bit and it also participate in powers of 2 to get your exact result. We can consider that extra bit. How that extra bit is saved in a computer? We will save, we will reserve one flip-flop. Okay, one flip-flop for storing that extra bit coming out of your n bits. Okay. So that is used for calculating overflow also. Okay. Apart from that carry extra bit, the computer will provide you one more bit after performing these operations between carry in and carry out of MSB, which we call that as an extra bit, which is overflow. Okay. So carry has to be considered for unsigned operations. Overflow has to be considered for signed operations. Okay. If overflow occur, it means magnitude bit is overflowed onto the signed bit, so the result is wrong. You should not consider for calculating your result. Okay. See, computer treat the numbers either unsigned or signed similarly, same way. Only the user has to interpret the result based on the type of numbers he is dealing with. Okay. That is what called overflow concept. So now this is what how we have to implement in computers. Okay. So not just the addition, similarly the procedure you need to carry out for even the subtraction also. Okay. Even when I subtract two positive numbers, obviously the result is less. We can represent within the range. Okay. When I subtract two negative numbers, obviously the result is also lesser than the minimum number. We can represent within the range. But when we subtract a positive number from a negative number, okay, when we subtract a positive number from a negative number, it is similar to we are adding two negative numbers. There is a chance of getting overflow. Similarly, when you subtract a negative number from a positive number, it is similar to we are adding two positive numbers and there is a chance of overflow. Okay, accordingly we have to deal with. Okay, so right. So these basic arithmetic operations now you want to perform with the help of computer, right? So while performing that with the help of computer, you should be clear what type of operation you are performing and what type of data you are using. Either it is signed or unsigned. Apart from that, it is also need to be considered whether it is fixed point or floating point, binary or BCD. Similarly, the characteristics are different. Okay. So now, next class we will develop a arithmetic processor which we call ALU, the heart, which computes the numbers. Okay, so we need to now design an arithmetic processor. Of course, the complexity is based on the type of arithmetic operations on which type of numbers you are performing. Okay, so initially we learn how to perform the basic arithmetic operations on sign magnitude integer data, mainly on integer data, that to sign magnitude representation. Later on we extend it to sign complement representation. Right. Okay, so initially we will use whatever we have to do till now, how we performed addition and all this knowledge. Basically this is used for building a hardware to implement any arithmetic processor. Okay, see, to design any hardware, first of all I should know how these operations are carried out in order to achieve a correct result. Okay, right? So any solution to the problem, you have to be started with some finite number of steps. Okay, we need to develop now an algorithm for performing the operation, how the step-by-step sequence that the computer has to follow. We humans know how to do this. So this is similarly the computer you wanted to do, right? So to implement this, we will develop certain algorithm which we call a series of a finite number of well-defined procedural steps. That's what an algorithm. We develop an algorithm to perform these. And finally, with the help of the procedure, we use to build a flow chart which consisting of modules, blocks like processing block, decision block. Okay. So usually the shapes of those blocks are already familiar to you. You would have written a flow chart in your C language and all. Okay, some rectangular boxes for specifying the computational steps, diamond shaped boxes for specifying the conditional. Okay, that indicates the decision, right? So some where each decision may be yes or no. Okay, right? So we develop various algorithms that shows the procedure that implementing in digital hardware. Okay, so we consider basic four arithmetic operations: addition, subtraction, multiplication, and division. How these are performed on fixed that to integer arithmetic. Okay, so those are sign magnitude separately and sign to complement separately. We will do. Okay, that's what a digital arithmetic, computer arithmetic that we see in next class. In next class, we start with the algorithm on addition and subtraction on sign magnitude data followed by sign to complement. Right. So today I just have introduced how can we perform operations on integer, signed and unsigned numbers. How can we interpret the result? Okay. So the concept of overflow I have introduced. Is that clear?
Yes, ma'am.
So please wait. I will collect the attendance from the chat window. Sixty-one, 62, 3, 4, 5, 6, 60, 69 absent, 72 absent, 80 absent, 82 absent, 93 absent, 97 absent, 100 absent, 108 absent, 113 absent, 115 absent, 116, 120. Okay, right? 1, 2, 3, 4, 5, 6, 7, 12 absent. Okay, Ma. So you can ask if you have any doubts. So otherwise, okay, shall I?
Thank you, ma'am.
Is there any doubts?
No, ma'am.